So we're going to talk about partial derivatives. So one of the basic questions, one of the main ideas in calculus is how do things change? How does a function change as the variable changes? And with multivariable functions, we can talk about change in various directions. So we don't just have a single derivative, we have multiple derivatives. So we can take the derivative with respect to x, with considering y a constant. We can take the derivative with respect to y, considering x a constant. So we have more things to keep track of. So today we're going to talk about what we call our first partial derivatives. So, and things get even more interesting when we start taking our higher order derivatives, and we'll talk about that tomorrow. So we have a multivariable function z, some function of x and y, and we're going to write our definition. The definition is going to look familiar, and you've done, or I guess I should be more accurate, you were assigned, right, Andrew? You were assigned homework problems where we calculated these using our definition. So our first partial derivative. So our first partial derivative with respect to x and we write it as f of x, or f sub x, I'm sorry. We can also write it as f sub x of xy. We can also write it as z sub x. And here's where fancy new symbols come in. This curvy d. So the curvy d reminds us that we're taking a partial derivative. So this is only with respect to x. So when we have a single variable function, there's no ambiguity. We can only take a derivative with respect to one of the variables, because that's the only variable we have. Yes?
Why don't you just write the regular d, and then if you just have d dx and d dy, then you know what it's respect to?
It's just to make sure that we're absolutely certain what we're talking about, just to avoid any kind of ambiguity. And we can also write this as lots of different ways. We can write this as dz, dx, or df dx. Yeah, this is our function is z equals f of xy. So we can write our first partial. These are all acceptable symbols for our first partial. The curvy d is, it really depends on the context, but I think the sub x notation is a little more modern, a little more like a current notation, where the curvy d is a little older notation. But you'll see them all. And this equals, and you're all familiar with our definition of the limit. Limit, or our derivative, limit as delta x approaches 0 of f of x plus delta x comma y minus f of xy all over delta x. And these are the homework problems. These are the homework problems that we did. We calculated a few of these. And with respect to y, it's the same thing. When we take our partial derivative with respect to y, our notation is the same. It's f sub y of xy, all the same, we just use our y rather than x. And if we have more variables, we have to have more, we have more partials. So if we write, and one reason we use the curvy D here is if you saw this without knowing anything else about the function, you would know immediately that this was a multivariable function because we have the curvy D, so that's telling us that we're taking the derivative with respect to just one of the variables. So if you saw this, you say your problem says assume that df dy is such and such. You know you're talking about a multivariable function. And this limit is just the same as the one for our partial with respect to x, but we're dealing with delta y. So this is f of x, y plus delta y, minus f of xy over delta y. So what we're doing is we're just taking the derivative with respect to one variable, assuming that the other variable is constant. We're holding the other variable constant is what we're doing here. And we'll do a couple of examples in a little bit. Any questions on this so far? Now if we want to evaluate our partial derivative at a point. At some point x0, y0. So we write the evaluation of our partial as dz dx at x0, y0. So kind of like our notation for evaluating a definite integral. And this we could also write as f sub x of x0, y0. And same thing if we're evaluating it, we're evaluating the partial with respect to y. So I just want you to be familiar with the different notation for evaluating our first partial derivative. And just as a note, as a reminder, to find f sub x, we consider y a constant. And to evaluate f sub y, we consider x a constant. So let's take a look at what this means graphically, just so we have a visual idea of what we're talking about here. Is everybody good with this? So graphically, here's our coordinate system. And here's our surface, our sum surface up here. And I'm going to draw a curve. And this, if I project this down onto my plane, oops. This is some y equals y0. Some line y equals y0. F sub x gives the slope of this curve. So we're holding y constant along this curve, and our partial derivative with respect to x gives the slope of this curve at a particular point. And if we look at a drawing for f sub y, we'll do that over here. And here's our surface. And we'll draw a curve along this surface going this direction. And we'll project that down onto the plane. And this line is x equals x0. The derivative with respect to y gives the slope of that curve. So we're holding x constant, and we're taking the derivative with respect to y, so it gives the slope of that curve. Does that make sense? So this is what we're looking at with our partial derivatives. So before we do any calculation, I want to, given the idea of what the partial derivatives are, what they give us, I want to look at a couple of examples for visualizing the partial derivatives. So in your book, on page 912, look at numbers 1 through 3. They give you a nice surface, and we just want to figure out if the sign of the partial derivative, particular partial derivative, is positive or negative at the point that they give you. Number 1 through 3. So they give you a nice surface there, and you want to figure out if the sign of the various partials that, at a particular point, the sign is positive or negative. And I think with multivariable stuff, it's really, if you have an intuitive idea of how to visualize some of these things, it really helps when you're solving problems. All right, we have some answers. So what do we think for number 1? The sign of the partial derivative with respect to x at 0.41. Positive or negative? So the back row says negative. Number one. So the second row says positive. What does the first row think? Positive. So let's see. So we're looking at that surface at 0.441. So we're going towards this 4 units on the x-axis and over 1 unit on the y-axis. So I think what that looks like to me is the surface in the above the first quadrant there is at a maximum at like 0, 0. So the derivative, so our slope would be negative. So the third row got that one. How about number 2? So we got a couple positives, a couple negatives. Second row says negative. You guys change your answer to positive?
No, Chris just shouted out things.
Oh, he shouted out things. I see. So you guys said negative. You said positive for number 2, and we're talking about the partial with respect to y at -1, -2.
I said negative. Was that, did I ask for that? I said negative.
You say negative.
You said negative.
You say positive. So let's see. We're looking at our surface at -1, -2. So we go back into the page on the x-axis, and -2 on the x-axis. And we want to figure out the partial with respect to y. And what did we decide? Positive. So that one should be positive.
Wait, why is it positive?
So if you go, let's see, -1. Oh, no, I'm gonna change my mind.
Yeah, does the beamer change his mind?
-1,
Scotty, does the beamer change his
-2.
No.
Right. So you want to figure out. So you're holding x constant. X is constant at -1.
Yeah.
So so you're going back into the page 1 unit,
Yeah.
and then you're going -2 in the y direction. So you're going to the left 2 units, and you're going up to your surface.
Yeah.
And up at that surface, the surface is at a high point, and if y is changing, you're going to be going from a higher function value to a lower function value. What's that?
Looks like the max
Why
is in
reaches the
between
maximum?
-1 and
What's that?
Wait, no, yeah, Scott.
But if we're thinking, think about how if our variable is increasing, going from the point where we're at, is a variable. So if we're going in increasing y direction, does the function go uphill or downhill? From -1, -2, going in the positive y direction?
Yeah, pizza.
Are there answers in the back? Like, do you have answers?
Uh-huh.
Can you see what the answer says?
What's
Wait,
your
so
interpretation?
what did we decide?
This is what it looks like, Mr. Beamer.
Scott.
Yeah, I know, Scott.
So you think it's going down a little bit there?
Wait.
Okay.
Yeah, so this
I-
is positive, right?
Okay,
here.
right. I see what you're saying, and that's negative. So, okay, so I would say I would say there's a little bit of ambiguity in the picture.
Art interpretation.
So unless we knew what the equation of the surface was, we couldn't be sure. So I will concede that there is some ambiguity in the picture there. It looks to me like it's decreasing there, but I could see how you could see it as increasing. All right, how about number 3?
So did we just decide number 2?
Number 2 is a little bit ambiguous based on the picture.
We're going to skip. All right.
Right.
Gotcha.
But the arguments, that's what the thinking about it, that's what we're trying to do. So
Don't you have like the
what's that?
bunch of answers?
Our arguments were just it looks like this, and it looks like this.
But you're looking at the surface, you're thinking about what the derivative with respect to y means at that point, and figuring it out. That's what I'm trying to get you to do is analyze those situations. The back of the book says negative. It does.
That's what's up. I'm right. Thank you, Scott.
But I think it's a little bit ambiguous. I think it's a little bit ambiguous. How about number 3?
Did you guys know that Star Wars has
Negative.
What's that?
Star Wars, the first one, The Phantom Menace, is coming to movie theaters
In 3D.
in 3D.
Yes.
They knew that.
All right, what do we come?
Negative.
What do we said? You said negative, Kaylin?
Yeah.
Some people say positive. What do you guys in the back say?
Yeah, but then if you're going this way, because you're changing in the Y, I would definitely say positive.
Positive. Looks like it's going uphill there. In the Y direction. We're going uphill in the Y direction. So we agree it's positive. Do we need to?
Oh, I get it. Or we're going this way.
Do we need to argue about that one?
Instead of like what we were even trying to do.
What do you think, Andrew?
I reckon it's going up.
It's wrong.
So if you were out for a stroll on that hill, you'd be going uphill. If you were going in the Y direction. Okay. All right. I reckon you're correct.
I reckon.
If you were coming uphill from that holler, right?
Okay, so then does that mean number 4 is negative?
Number 4.
We didn't do that.
We didn't do number 4. Let me look at number 4. I didn't think about number 4.
I'm understanding now. This is great.
Good. So now, then we'll talk about the next ones, and hopefully it'll all be crystal clear.
Or negative.
Let me look. I didn't look at that.
Yes.
Number 4, -1, -1. So there was some ambiguity in number 2. Let's look at number 4. What do you think on number 4?
Negative.
Negative, is that the...
That whole slope is going down, that whole
Right.
little section.
All right.
In the x direction, yeah, we'd be going downhill there. All right. Now we're going to look at it a different way. Look at the derivatives a different way. Number on page 913. Look at number 49 and number 50. So on number 49 and number 50, we're looking at graphs of the partial derivatives, and we want to decide if those graphs represent the partial with respect to x or the partial with respect to y of that surface.
This is so hard. I don't know. Okay. Is the first one X? No, I should. I don't know. First one's X.
So on number 49, you look at the graphs of the derivatives and see if that represents a graph of the partial with respect to x or the partial with respect to y.
I really don't know.
B. B is the X.
So Anne
Have that position.
Anne says, so is this a consensus of the first row? Danny still can.
X is the first one.
So we got a couple of people saying that the first is the derivative with respect to x, and a couple that are saying the first is the derivative with respect to y.
No.
All right, so let's talk about the first one, a. What do we think about a? X, y, x, y.
God agreed with me.
So on that first surface, or on the surface, if you're talking about the derivative with respect to x, so if you're moving along in the x direction, keeping y constant. So think about, just to make it a little easier, think about right along the x-axis. So for positive x, is the slope there positive or negative?
Negative.
Negative. With respect to x, the slope is negative. For negative x, the slope is,
Negative.
we start going uphill.
Yeah.
So which graph of the partial changes from positive to negative as you go from positive x to negative x? The second one, right?
So we were right.
So the second one should be the partial with respect to x. The first one is the partial with respect to y. If you think about the derivative with respect to y, it's positive for negative y and negative for positive y. So that would be the first graph.
Okay.
Now look at number 50. 50 is a little more challenging.
I think the first one's Y, so I'm probably gonna be wrong.
So we have one opinion for A is the partial with respect to y.
I'll change my mind.
Sure, you can change your mind.
I have absolutely no idea. These do not make sense.
I'm gonna say A is X. But I don't know for sure.
All right, so let me give you a pointer here. For the surface, if you let's look at the partial with respect to x. So looking at the graph of the surface,
Yeah.
if you're moving in the positive x direction, are you going
Going up.
uphill or downhill?
Up.
So your partial with respect to x, if you're going uphill, your derivative is positive or negative? Positive. If you're going uphill, your derivative is positive. So if you're going uphill,
So X is A.
x is a because that one's always positive, right?
Yeah.
The slope is always positive. So that would be the derivative with respect to x. So b would be the derivative with respect to y. That one takes a little more analysis. All right, let's do some examples of calculating. I liked the discussion. What's that?
No.
This is
Oh
block
my
day.
God, it's Thursday? What? We're out.
Good show.
God, so I'm in here till like 9.
I know, it's terrible, isn't it, Caitlin?
So long. It's just long when you thought you were
You thought you were done?
half an hour. Now I have like another half hour.
Yeah, I should have put the microphone on omnidirectional, so it got the whole class for that whole
I
thing.
wasn't like mentally prepared to have blocked this.
Do we need to take a break, Caitlin?
Yeah.
Should we take a 5-minute break? Okay, we can take a 5-minute break. Why don't we do that?
Minute mental break? Okay.
Yes.
Are we watching one?
No, I record the lectures and post them on YouTube. That type of, that type, yeah. All right, let's do some calculations. We have a function h of xy is x squared minus y squared. We want to find f sub x and f sub y at negative 2, 1, 3. So we have this surface and we want to find our slopes at a couple of different points. Before we do our calculation, what kind of surface is this? It has hyperbolas in it. Hyperbolic paraboloid. So Tian sees the graph in the book. This is a problem from the book. All right, so let's calculate our partials. So dh dx. dh dx is going to be what? 2x if y is constant, derivative of a constant goes away. So that our derivative with respect to x is just 2x. Dh dy minus 2y, yes. And then to find at our point, so at negative 2, 1, 3, f sub x is going to be, plug in negative 2 there, and we get negative 4. And f sub y, plug in 1 here for y, and we get negative 2.
Is that all?
Yep, that's all that's involved in that one. Let's look at another example. So calculating is pretty straightforward as long as you remember that when you're calculating your derivative with respect to x, y is constant. When you're calculating with respect to y, x is constant. So let's look at z equals cosine of 2x minus y. And we want to find our partials at, first partials at pi over 4, pi over 3, and square root of 3 over 2. So our partial with respect to x is going to be what? Minus sine 2x minus y. Are we missing anything? Times 2. So minus 2 sine 2x minus y. And at pi over 4, pi over 3, square root of 3 over 2. So we're just going to substitute our x's, our x and y in here. We calculate this, so at our point, we get minus 2 sine of 2 times pi over 4 minus pi over 3. And if we simplify that, we get minus 1. And our partial dz dy. What do we get for dz dy? Sine of 2x minus y. And at our point, we substitute that in. Substitute our coordinates in. And we simplify, we end up with 1/2. Let's do one that's a little more challenging. The calculating the partials is not a little more challenging, but the idea of the problem is. Did anyone have questions before we move on? All right, so we have f of xy equals 3x squared, 3x cubed, sorry, couldn't read my writing, minus 12xy plus y cubed. And we want to find where f sub x and f sub y are 0 simultaneously. So we want to find where our first partials are both 0 at the same time. What would you guess happens at a point like that? Is it flat? So if you had a surface, what would that be on your surface? Could be at the origin.
The top of 37.
So Scott says the max or the min. So this is going to be where we have a possible maximum or minimum in our surface. All right, so let's calculate our partials. Our partial with respect to x is what? 9x squared minus 12y. Uh-huh. And our partial with respect to y? Minus 12x plus 3y squared. And we want these to be 0 at the same time. So I'm going to use the first one to solve for one of the variables, and we'll substitute. So we have 9x squared minus 12y equals 0. And if I solve this, I get, solve this for x, I get x equals y squared over 4. Divide everything by 3.
So then when you have x squared minus
Oh, sorry. No, I'm jumped ahead. This is my I solved my y equation here. All right. Sorry, I jumped ahead a step. So this gives me 3x squared. 3x squared equals 4y. 3x squared is 4y. And the second one gives me minus 12x. I'm sorry, 12x equals 3y squared. If I set the second one equal to 0, the partial with respect to y. This is the one that gives me x equals y squared over 4. And I'm going to substitute now. Substitute for x here. So substitute. So I get 3 times y squared over 4 squared equals 4y. So 3y to the 4th over 16 equals 4y. And when I solve this, I end up with 3y to the 4th minus 64y equals 0. And I can factor out a y. So y times 3y squared minus 64 equals 0. So y equals 3y cubed. Yes, thank you. So finally, y equals 0, or y equals 4 over 3 to the 1/3. And this tells me that x equals 0, or x equals 4 over 3 to the 2/3. So our points are where the first partials are 0 simultaneously, are 0, 0, and 4 over 3 to the 2/3, 4 over 3 to the 1/3. So both of those points, the first partials are 0 simultaneously. And that's in your book, number 46. They have a graph. They have a graph of that surface on page 912. So if you want to look at what that surface looks like. Oh, sorry, they don't have a graph of that surface. Would we like to see a graph of that surface? Okay. I'm going to do it. I'll grab my tablet and we'll look at a graph of that surface. Let's see. That's all I have for today. So let me put the homework up and then I'll go grab my tablet. All right, there we go.